Welcome to Star Stuff. My name is Dr. Yadav Pandit. Today, we embark on a journey exploring the lives and deaths of stars, focusing intensely on the critical role that a star's mass plays in its entire life story. Our goals for learning are to answer a few fundamental questions. First, how does a star's mass affect nuclear fusion? Second, what are the life stages and ultimate fates of both low-mass and high-mass stars? And finally, how can close stellar companions alter these usual life stories? Stellar mass is the master key. The mass of a main sequence star fundamentally determines its core pressure and temperature. Stars of higher mass have hotter cores and more rapid fusion rates. This makes them both more luminous and significantly shorter-lived. In contrast, stars of lower mass have cooler cores, slower fusion rates, smaller luminosities, and consequently, much longer lifetimes. We learn about these processes by comparing mathematical models of stars with observations, especially those made of star clusters. Star clusters are particularly useful because they contain stars of different masses that were all born at about the same time. Let's trace the life track of a low-mass star, such as our Sun. A star begins on the main sequence as long as it fuses hydrogen into helium in its core. When the star can no longer fuse hydrogen to helium in its core, the core shrinks and heats up. Observations of star clusters show that the star becomes larger, redder, and more luminous after its time on the main sequence is over. It enters the red giant phase. As the core contracts, hydrogen fusion begins in a shell around the core. The core thermostat is broken, meaning the increasing fusion rate in the shell does not stop the core from contracting, and the luminosity sharply increases. Helium fusion requires higher temperatures than hydrogen fusion due to the greater charge, leading to greater repulsion. Furthermore, fusion of two helium nuclei doesn't work, so helium fusion must combine 3 helium nuclei to make carbon. In a low-mass red giant, the core thermostat is broken because degeneracy pressure supports the core. When the core temperature finally rises enough for helium fusion to begin, the fusion rate rises very sharply. This rapid process is known as the helium flash. The helium fusion rate skyrockets until thermal pressure takes over and expands the core again. After the flash, the thermostat is temporarily fixed, and the helium fusion star neither shrinks nor grows. Models show the star shrinks and becomes less luminous, moving to the horizontal branch on the HR diagram. So, how does a low-mass star die? When the core runs out of helium, it enters the double shell fusion stage. Helium fuses into carbon in a shell around the carbon core, and hydrogen fuses to helium in a shell around the helium layer. This stage never reaches equilibrium, resulting in a series of thermal pulses. Fusion progresses no further in a low-mass star because the core temperature never grows hot enough for the fusion of heavier elements, though some helium fuses with carbon to make oxygen. Double shell fusion culminates with a pulse that ejects the hydrogen and helium into space as a planetary nebula. The core left behind becomes an inert white dwarf, supported against gravity by degeneracy pressure. For a sun-like star of 1 solar mass, its luminosity will rise to 1,000 times its current level, too hot for life on Earth. The Sun's radius will also grow to near the current radius of Earth's orbit. Now, let's turn our attention to high-mass stars, which are defined as those greater than 8 solar masses. High-mass main sequence stars fuse hydrogen to helium at a higher rate using the CNO cycle, where carbon, nitrogen, and oxygen act as catalysts. Greater core temperature is what enables hydrogen nuclei to overcome the greater repulsion involved in this process. The late life stages of high-mass stars are similar in pattern to low-mass stars, beginning with hydrogen core fusion, followed by hydrogen shell fusion, and then helium core fusion. But they become supergiants. High-mass stars are the factories for the heavier elements. Recall that the Big Bang made only 75% hydrogen and 25% helium. Stars make everything else. Higher masses produce higher core temperatures, enabling the fusion of heavier elements. These stars engage in helium capture, where high core temperatures allow helium to fuse with heavier elements, building carbon into oxygen, neon, and magnesium. In stars greater than 8 solar masses, core temperatures allow for advanced nuclear fusion. This fusion makes elements as heavy as iron, such as silicon, sulfur, calcium, and iron. This advanced fusion proceeds in a series of nested shells. Iron is the critical turning point. It is a dead end for fusion. Nuclear reactions involving iron do not release energy because iron has the lowest mass per nuclear particle. When iron builds up in the core, Degeneracy pressure can no longer resist gravity, and the core suddenly collapses. The degeneracy pressure disappears because electrons combine with protons, creating neutrons and neutrinos. The collapse of the core creates a supernova explosion. The neutrons collapse to the center, forming a neutron star. The energy and neutrons released in this explosion are what enable elements heavier than iron to form. The star's outer layers are driven into space, forming a supernova remnant, such as the Crab Nebula. While mass determines a star's entire life story, the lives of stars with close companions can be different. Stars in close binary systems can exchange mass, altering their usual evolution. Consider the binary system Algol, which currently consists of a 3.7 solar mass main sequence star and a 0.8 solar mass subgiant star. This is strange because the lower mass star is further along in its evolution. The explanation is that the star now identified as a subgiant was originally more massive. As it reached the end of its life and started to grow, it began to transfer mass to its companion, making the companion star now more massive. To summarize, mass determines how high a star's core temperature can rise, and therefore determines how quickly a star uses its fuel and what elements it can ultimately make. Low-mass stars end as white dwarfs after ejecting a planetary nebula, while high-mass stars create elements up to iron and end their lives dramatically in supernova explosions, leaving behind a neutron star or potentially a black hole. Thank you for joining this lecture on Star Stuff's